Hello, everyone. Well, we've been talking about integration on the circle, and I've suggested to you that for physics, this is going to be important because it extends to integration on spheres, and spheres are very important for quantum mechanics. But it also extends to give us integration theories on more general objects, including relativistic circles and spheres, which are ultimately groups which are very important in physics. And more generally, I want to talk today a little bit about something of a grand aim that I have, a rather ambitious aim of trying to explore to what extent we can help physics along or provide some interesting new directions by thinking a little bit more carefully and deeply about the associated mathematics. So I'm a mathematician, not a physicist. But some of the mathematics that I've done over my career is actually quite closely connected to physics, in particular to quantization, and the representation theory that I've been involved in is very close to that, used in both quantum mechanics and relativity and the Standard Model. So what I'm hoping for is that we'll be able to use pure mathematics as something of an additional laboratory. So right now, theoretical physics at the highest level, dealing with really foundational issues, is in a bit of a dilemma because it appears as if the prime places where important new data can be obtained, namely accelerators like the Large Hadron Collider, or telescopes peering into the early part of the universe where issues of particle physics are very important. These are both very expensive developments, and it seems to be very challenging to push things further into energy realms where physicists might be able to extract important new information. What I want to suggest to you, and it's not a new idea, of course, but I have some new ideas in this direction, is that modern pure mathematics also, in fact, in a surprising way, provides something of a theoretical laboratory, potential laboratory, to understand some important issues in modern physics having to do with quantum mechanics, relativity, both special and general, and the Standard Model. And in particular, the areas that I think are perhaps most fruitful are those associated with representation theory of Lie groups. Now, this is a topic which developed hugely in the 20th century, work of Killing and then Cartan and notably Hermann Weyl and then many other people. It's become a sort of a centerpiece for that area intersecting physics and mathematics. And it's perhaps not widely appreciated amongst physicists that there's an aspect of this representation theory story in which quantum mechanical ideas arise very naturally on their own, essentially completely independently of their development in physics. And somewhat coincidentally, this was first sort of started to be appreciated around the 1930s, which was pretty well also the time when quantum mechanics was being solidified. So what am I talking about here? I'm talking about a topic in mathematics called quantization, where the analog between a classical mechanical system framed in a Lagrangian or a Hamiltonian fashion. So these are variants of ways of describing Newton's laws developed by Lagrange and Hamilton. They have a different flavor. So the Hamiltonian formulation rests on sort of symplectic manifolds, Poisson brackets, and things like that. And while the Lagrangian point of view is resting on the principle of least action and sort of has a Lagrangian at the center stage, while the Hamiltonian version, one has a Hamiltonian. Now, both of these approaches turned out to be important in quantum mechanics, and the smoke perhaps hasn't cleared to ultimately decide which one of these, if any, is going to be ultimately more insightful. But the Hamiltonian point of view in particular turns out to have a very strong connection with Lie group representation theory. And I want to talk a little bit about that today, just to give you sort of an overview and perhaps some motivation for why it's going to be important for us to think about Lie groups and issues of integration and harmonic analysis on Lie groups in a way that will help physicists. So when we're talking about Lie groups, maybe it's useful to restrict ourselves to relatively simple ones. We're talking about groups which have a continuous or actually differentiable kind of aspect. And the circle S1 is a prime example. The three sphere S3, commonly called SU2, is in some sense the next one up. It's sort of the first non-commutative Lie group. And it's crucially important and very interesting. And basically the entire theory of quantum theory of the hydrogen atom and, these sp-df orbitals that are crucial in quantum chemistry, they all are arising essentially from the representation theory of SU2 and associated spherical harmonics. SU2 also figures in the standard model along with S1, so S1 and SU2 and SU3. S1 roughly describing as the gauge theory for electromagnetism, and SU2 for the weak interaction, and SU3 for the strong interaction. And these three Lie groups sort of coincidentally are arguably sort of the simplest Lie groups roughly, that one can study, sort of starting from the very simple S1, which is commutative, and SU2 and then SU3. But there's a big step from each one of those to the next one, okay? A big step from S1 to SU2, and another huge step from SU2 to SU3. And one shouldn't think that once one has understood SU3, one understands the general situation. Going out to exotic groups, notably E8, just sort of looming on the horizon there as an object that one wants to understand, and which is becoming very important in modern physics, particularly due to the very interesting work of Gerrit Lisi. So if we restrict ourselves to S1, SU2, and SU3, which are sort of the core Lie groups connected with the standard model, and we might think of these as sort of local symmetries of spacetime, symmetries that have something to do with sort of a structure that's somehow intrinsically localized at points, as opposed to sort of large-scale symmetries of spacetime more generally, usually associated, say, with the Lorentz group or the Poincare group. Those groups are also very important. So when we study harmonic analysis on these things, especially when we go to the non-commutative settings, there's a well-established theory, okay, and there's a famous theorem of Peter-Weyl, which describes the representation theory and construction of representations, say, of a compact, simple Lie group like SU2 and SU3, sort of geometrically. And it turns out that this description has an interesting sort of quantum mechanical aspect. And that became clear late in the 60s when Kirillov was investigating the irreducible representations for nilpotent groups, which is an entirely different class of groups, and found remarkable correspondence between irreducible representations and so-called coadjoint orbits. So what is a representation? A representation is kind of a manifestation of a group in the world of linear algebra. So you have a group with operations, and you try to make that explicit by getting explicit matrices of a particular size, which encode the group relations. In other words, you're realizing the group as a group of matrices. So that's called a representation. And a given group, like SU2, can have lots of different representations. And I've talked about this in various places. So for SU2, it's particularly interesting and simple. There's sort of one irreducible representation in every dimension, and that's all. For SU3, it's more complicated, and for E8, it's much more complicated. But still, there's a reasonably well understood theory that covers the entire representation theory of compact Lie groups, at least up to the point in terms of classification and corresponding characters, which are sort of the elementary building blocks for harmonic analysis on these things. And what Kirillov discovered is that these coadjoint orbits in the nilpotent case that were naturally corresponding with these irreducible representations in the nilpotent case were like classical mechanical systems. And the association of representations to these coadjoint orbits was very much in line, analogous to the way physicists constructed quantum mechanical systems from classical mechanical systems. That going back to Heisenberg, really, and his matrix mechanics. So Heisenberg initiated this idea that instead of classical observables like position and momentum, say of a particle moving along a line, in the quantum mechanical framework, one rather wants to consider operators. Think of position and momentum rather as operators, operating in some actual linear space, which is in principle infinite dimensional, so much more complicated, but still simpler in some fashion because we're still just using linear algebra. So the geometry that you might associate with a curved space gets transformed into linear algebra, even though you may have to go up in dimensions to capture the full richness. So this is a very interesting story and the beginning of a program in mathematics called quantization or geometric quantization. And a lot of people, Kostant and Souriau, contributed along with Kirillov to develop a kind of a recipe, a very broad kind of recipe for connecting the mathematical equivalents of classical mechanical systems, which were coadjoint orbits. These are sort of orbits in the group in the dual of the Lie algebra, and then the irreducible representations. So what I would like to do is ultimately I'd like to explore this, and with the view that what would have happened if in the 1930s physicists hadn't discovered quantum mechanics and had just been keeping on going with classical mechanics, and the mathematicians had started to develop the representation theory, and they would have basically discovered at least aspects of quantum mechanics directly from the mathematics associated with these purely abstract objects, these Lie groups and their associated representations. Now, we don't know how that story would have gone, but I think it's a powerful thing that physicists should be aware of, that the mathematical universe has encoded within it, many aspects of the quantum mechanical universe. So if we're thinking about quantum mechanics as being some deep and abiding mystery, and we're really racking our brains to try to understand what it really means, so we have all these different interpretations of quantum mechanics, right? One way of perhaps shedding light on this is to look at the corresponding mathematics and say, well, let's understand what's going on there in a better, more profound way, right? If we've done that, then maybe the mathematics itself will reveal ways of thinking or will reveal avenues of exploration that will be then translatable into physics and physics understanding and progress. So that's more or less the reason why I want to slowly and somewhat systematically and perhaps in a novel way develop fundamental aspects of harmonic analysis, starting with the circle, but you have to get the circle right. And then we're in a position to go to SU2, and then we'll be in a position to go to SU3. And down the road, I know it's a long road, but down the road, we'll even be able to think about E8, which would sort of like the holy grail in this subject, to try to understand E8. And does it really hold the key or a key to understanding the world in which we live in? I'm not saying it does, but I'm not saying it doesn't. So lots to think about, and I'm hoping you're going to be joining me on this adventure and contributing and and helping me move into interesting waters.